7 visitors are racing toward Earth. It sounds like science fiction, yet it's undeniably real. By the end of 2025, 7 substantial comets will descend upon the inner solar system within a mere 6-month window. This phenomenon is so extraordinarily rare that leading astronomical surveys like Pan-STARRS and Atlas have never documented anything remotely comparable. Hidden among these travelers is 3 I/Atlas, only the third interstellar comet humanity has ever identified. Its exotic chemical composition and massive green coma mark it as the ultimate cosmic enigma. The probability of such an event occurring by pure chance? Less than 0.5% per decade. Are we witnessing an astronomical coincidence of epic proportions, or is something unfolding that defies the established patterns of our celestial neighborhood? The answers and the implications begin here. Every night, an intricate network of digital sentries scans the heavens. These are the world's automated comet detection systems. Pan-STARRS, Atlas, and their counterparts position atop remote mountain peaks in Hawaii, Chile, and South Africa. These sophisticated telescopes methodically survey nearly the entire visible sky night after night, capturing faint glimmers that will elude even the most experienced human observer. Their imaging sensors possess the sensitivity to detect objects as dim as magnitude 21, vastly fainter than Pluto appears from our vantage point on Earth. Each captured image represents a mosaic containing millions of stars and distant galaxies, but the true prize lies in detecting movement. A single pixel shifting position from one frame to the next, revealing the presence of a previously unknown comet. The surveillance process operates relentlessly. Pan-STARRS and Atlas function on a precise schedule that encompasses most of the observable sky every 2 to 3 nights. Their sophisticated algorithms compare each fresh image against an extensive digital archive of the cosmos, instantly flagging any object that has changed position. Once a potential candidate emerges, a cascade of coordinated activity commences. Automated alerts dispatch across global networks. Rapid follow-up observations mobilize telescopes worldwide, and astronomers race to confirm the discovery before the object fades into the cosmic background. This digital vigilance has fundamentally transformed the field. 2 decades ago, discovering a comet required months of patient manual observation and considerable luck. Today, the discovery rate has nearly doubled with each passing year. Faint, distant visitors that once passed by undetected are now systematically cataloged, tracked, and analyzed in real time. The Minor Planet Center maintains detailed records of each detection, constructing an ever-growing census of icy wanders that expands by hundreds annually. Yet despite this unprecedented capability, even the most advanced surveys typically identify no more than a couple of bright comets during any single observing season. The clustering of 7 significant comets in late 2025 pushes far beyond the operational parameters these systems were designed to handle. Engineers and telescope operators, usually content to let automated algorithms manage the workflow, now find themselves monitoring their displays intently as the data pipeline illuminates with more comet alerts than anyone considered possible. For the first time in the modern era, the machines are struggling to keep pace with what the sky is revealing. Before we delve deeper into this extraordinary celestial convergence, it's worth establishing a fundamental vocabulary. Comet science employs its own specialized terminology, though most concepts are more straightforward than they initially appear. Perihelion refers simply to a comet's point of closest approach to the sun, the critical juncture where intense sunlight transforms a frozen nucleus into a spectacular display of vaporized gas and suspended dust. This term appears in virtually every comet forecast because it marks the moment when peak activity occurs. Distances within the solar system escalate rapidly, so astronomers employ the astronomical unit AU as standard shorthand. 1 AU equals the distance from Earth to the Sun, approximately 93 million miles, or 150 million kilometers. When a comet's perihelion registers at 25 cents, this indicates it will pass at 1/4 the distance from the Sun to Earth's orbit. For observers hoping for a visual spectacle, closer perihelion distances generally translate to brighter displays. Regarding brightness, astronomers rely on the magnitude scale as their universal measurement system. Here's the essential concept. Lower numerical values indicate brighter objects, A magnitude of 6 represents the faintest threshold most people can perceive without optical assistance under pristine dark skies. A magnitude of 3 or 2 becomes bright enough to capture the attention of anyone stepping outside during dawn or dusk hours. Some comets, given favorable conditions, can even outshine the most brilliant stars in the night sky. Then there's the matter of tails. Every active comet develops at least one tail as it approaches the sun, and frequently 2 distinct types emerge simultaneously. The dust tail appears broad and pale, composed of microscopic particles gradually pushed away by the physical pressure of sunlight itself. The ion tail manifests as a straight, narrow beam of electric blue, formed from charged gas molecules swept directly by the continuous stream of particles flowing from the sun, the solar wind. Consider it a cosmic windsock indicating space weather conditions in real time. Occasionally, a powerful solar storm will sever an ion tail completely, only for the comet to regenerate it within mere hours. These tail disconnection events occur rarely, but with 7 comets simultaneously occupying the inner solar system, 2025 could deliver multiple such events captured on camera in real time. Keep these fundamental concepts in mind. They'll prove invaluable for interpreting every news headline, every star chart, and every surprise these 7 visitors have in store. Statisticians who analyze comet survey data sometimes quip that the universe proves remarkably stingy with surprises. During a typical 6-month observation window, probability models suggest we should anticipate 2, perhaps 3 comets bright enough for amateur backyard telescopes to observe comfortably. The remainder stay faint, remain distant, and ultimately reside only in the minor planet center's extensive archives. Late 2025, however, completely overturns these expectations. 7 significant comets, each with perihelia compressed into a single 6-month period, have triggered alarm conditions in every Monte Carlo simulation executed by comet population modeling specialists. The statistical evidence proves stark. Throughout the past decade, advanced digital surveys have elevated the detection rate of faint comets to unprecedented levels. Yet even with optimal technology deployed, computational simulations demonstrate that a cluster of 7 comets appearing in one season constitutes a profound statistical outlier. When researchers input actual survey sensitivity parameters and current comet population estimates into their models, the median expectation yields merely 2 to 3 significant comets per 6-month window. The probability of encountering 7? Less than 0.5%. Some simulation runs produce odds approaching 1 occurrence per 1,000 years for a grouping exhibiting this collective brightness. This rarity doesn't stem merely from improved camera technology or more vigilant software algorithms. Bright comets are fundamentally governed by the physics of their orbital mechanics and the inherent randomness of gravitational perturbations that occasionally nudge them sunward. Enhanced survey efficiency enables detection of more faint wanderers, but it cannot conjure into existence a coordinated arrival of 7 major visitors. The 2025 lineup stands distinctly apart from any event logged during the digital astronomy era, and even historical photographic records struggle to identify a comparable precedent. For data scientists and statistical astronomers, this represents a variety of anomaly that demands thorough investigation. Are we observing the delayed aftermath of a distant collision in the outer solar system? An improbable fluctuation in Oort cloud dynamics? Or simply a cosmic coincidence so exceedingly rare it nearly appears choreographed? Whatever the underlying cause, the numerical evidence remains unambiguous. 2025's comet convergence represents the astronomical equivalent of winning the celestial lottery, an event modern astronomy has never before witnessed. Some comets traverse the solar system virtually unnoticed, their feeble glow lost against the stellar background. Among 2025 7 visitors, 2 fall into this understated category. C/2022 Pan-STARRS and 240P/NEAT. C/2022 Pan-STARRS reaches perihelion on July 31st, passing approximately 3.82 astronomical units from the Sun, well beyond Mars's orbit, approaching the distance of Jupiter. At such remote separation, sunlight barely disturbs the icy surface. The result manifests as a modest coma, visible exclusively through telescopes equipped with highly sensitive detectors. Most amateur observers won't perceive more than an indistinct smudge, even under the clearest atmospheric conditions. 240P/NEAT, a periodic returning visitor, executes its solar passage on December 19th at 2.12 astronomical units, still twice Earth's distance from the Sun, a separation clearly reflected in its subdued brightness. This comet has completed this journey previously, each apparition offering a low-key encore for those dedicated observers willing to pursue it across winter skies. For both objects, the primary audience consists of devoted amateur astronomers who systematically log observations, digitally stack multiple exposures to enhance faint details, and exchange findings through online communities. Their patience fills out the faint end of the comet's census, ensuring that even the quietest visitors receive proper documentation. While these two comets won't command headlines or capture public imagination, they underscore the full spectrum represented within the 2025 lineup. From telescopic whispers barely above detection thresholds to headline-grabbing spectacles, their presence establishes the baseline for brighter, more dramatic arrivals yet to come. For anyone who has ever gazed upward and wished for a comet brilliant enough to rival the brightest stars, late 2025 delivers far more than faint hope. 3 of the 7 visitors, C/2025 R2 Swan, C/2025 Atlas K1, and C/2025 A6 Lemon, are developing into genuine crowd pleasers, each bringing its own promise of celestial theater. Swan, officially designated C/2025 R2, executes its closest approach to Earth on October 21st, passing at merely a quarter of an astronomical unit, approximately 37 million kilometers. This proximity allows the solar wind to sculpt a dramatic tail structure while achieving sufficient brightness that even casual observers might glimpse it at dawn without optical aid. Outgassing models predict Swan could attain magnitude 2 or 3, a brightness level that transforms comet observation from specialized hobby into neighborhood event. Just weeks later, Atlas K1 plunges inward, reaching perihelion on October 8 deep inside Mercury's orbit. The intense solar radiation at 0.33 astronomical units should trigger activity levels into overdrive, unleashing powerful jets of sublimating gas and suspended dust. Astronomers anticipate an expansive tail structure and a variety of unpredictable outbursts that generate headline photographs and captivate public attention. Then arrives Lemon, C/2025 A6, making its closest solar approach on November 8th at slightly more than half an astronomical unit from the sun current forecast, suggests it could brighten to magnitude 4, possibly even reaching 3.5, rendering it visible during evening twilight across the northern hemisphere, and an ideal target for backyard binoculars or small telescopes. Each of these comets carries distinct characteristics. Swan's close Earth approach, Atlas K1's inter-orbit fireworks display, and Lemon's classic evening apparition all offer opportunities for something genuinely rare. A comet so bright that telescopic equipment becomes optional rather than mandatory for observing the show. Not every comet in the 2025 lineup achieves optimal visibility from Earth's surface. Some, like 414P/stereo, remain practically invisible to ground-based telescopes while occupying center stage with a fleet of spacecraft positioned around the Sun. On September 27th, 414P/stereo swings past at just over half an astronomical unit from the Sun, closer than Venus's orbit. However, its trajectory keeps it positioned within the Sun's glare from our terrestrial vantage point. This scenario perfectly suits missions like the Solar and Heliospheric Observatory, SOHO, and the Solar Terrestrial Relations Observatory, STEREO. They're specialized cameras, designed primarily for monitoring solar storms and coronal activity, capture comets as brilliant streaks traversing the solar corona, revealing activity details that ground-based observers miss entirely. Mission teams at NASA and the European Space Agency are already managing complex observation schedules, carefully weighing which comets receive precious instrument time from their limited resources. October sky will be extraordinarily crowded, not merely with comets, but with competing scientific priorities demanding attention. Swan and Atlas K1 promise dramatic tail evolution and dynamic activity, while 3i/Atlas, the interstellar newcomer, demands intensive scrutiny during its brief passage through the inner solar system. Each spacecraft operates with constrained field of view and can target only one object at any given moment. This constraint necessitates difficult decisions. Should instruments focus on documenting the unprecedented interstellar chemistry of 3I/Atlas, or should they track the evolving tail structures of Swan and Atlas K1, as both respond to varying solar wind conditions and potential coronal mass ejections? Heliospheric imagers and coronagraphs will track tail disconnection events in real time, capturing the precise moment when a solar eruption severs a comet's ion tail. These observations transcend mere spectacle. They reveal fundamental processes of how the sun's magnetic field sculpts comet tails and, by extension, illuminates the invisible space weather environment that permeates our solar system. In 2025, spacecraft instruments and ground-based telescopes form an integrated observational network, each covering angles and wavelengths the other cannot access, ensuring that no visitor passes through unstudied or undocumented. 7 comet arrivals, all compressed into a single calendar stretch. From late July through December, the inner solar system transforms into a cosmic thoroughfare unlike anything witnessed in living memory. The first visitor, C/2022 Pan-STARRS, executes its distant passage in July, barely registering on detection equipment. Then the pace accelerates dramatically. By September, Swan approaches rapidly, followed closely by 414P/Stereo, which slips past the sun while spacecraft scramble for optimal observation positions. October becomes genuinely crowded. Atlas K1 dives toward the sun, outgassing furiously as it penetrates deep inside Mercury's orbit. Mere days later, 3I/Atlas, the interstellar outlier, threads its hyperbolic trajectory past Mars, its coma swelling to hundreds of thousands of kilometers in diameter. Lemon follows in November, drifting into dusk skies with the promise of naked-eye visibility for millions of potential observers. Finally, in December, 240P/Neat completes the sequence, a quiet encore for those still monitoring the skies. Displayed on a temporal timeline, these arrivals appear less like random scatter and more like a cosmic choreography. Each comet's perihelion falls within weeks of the next, leaving minimal downtime for professional astronomers or amateur sky watchers. This compressed schedule generates overlapping observation campaigns, saturated data processing pipelines, and a continuous stream of fresh imagery requiring analysis. For the first time in modern astronomical history, the challenge isn't locating a comet in the vast sky. It's maintaining accurate records of which specific comet you're currently observing. This 6-month compression transforms the night sky into a dynamic laboratory where the physical mechanics of coma development, tail formation, and solar wind interaction play out in real time, occasionally with multiple comets visible within the same photographic frame. The stage has been set for a season of tail physics and solar dynamics unlike anything recorded in recent memory. Every comet in the 2025 lineup brings distinctive features to the night sky, but nothing distinguishes them more dramatically than the twin tails that stream behind. The fundamental difference derives from what material is being expelled and which force drives that expulsion. The dust tail appears broad and gently curved, composed of microscopic particles swept away from the comet's surface by the physical pressure of sunlight itself, radiation pressure. These minuscule grains scatter incoming sunlight in all directions, producing a pale, sometimes golden, luminescence that can extend for millions of kilometers. It fans out gradually behind the comet, following the curvature of its orbital path like a luminous wake trailing through space. The ion tail, by contrast, manifests as a straight, narrow blade of electric blue light. This tail forms when intense ultraviolet radiation from the sun strips electrons from gas molecules within the coma, ionizing them into electrically charged particles. The solar wind, a relentless stream of charged particles racing outward from the sun at hundreds of kilometers per second, captures these ions and accelerates them directly away from the solar surface, regardless of the comet's direction of motion. The result, a tail that invariably points straight away from the sun, often exhibiting sharper definition and more vivid coloration than its dust counterpart. For visual observers, the distinctive characteristics are unmistakable. Dust tails appear wide, soft-edged, and typically yellowish or white in color. Ion tails present as thin, straight, and blue. Each tail narrates a different physical story about the forces at work, and both remain vulnerable to the sun's volatile temperament. When a powerful solar storm sweeps through the inner solar system, an ion tail can be severed in mere moments, a dramatic event that reveals just how dynamic and unpredictable these cosmic visitors truly are. With 7 comets navigating the inner solar system simultaneously, 2025 offers unprecedented opportunities to witness these spectacular disconnection events. Solar storms don't merely illuminate Earth's auroras. They can transform a comet's graceful tail into a cosmic battlefield. When a powerful coronal mass ejection, CME, sweeps through the inner solar system, it drags the sun's twisted magnetic field along for the journey. If a comet happens to occupy the storm's trajectory, the results prove spectacular. The ion tail, that straight blue blade pointing directly away from the sun, can be completely severed within minutes. This isn't a gradual fading or slow unraveling. One moment, the tail stretches across millions of kilometers. The next instant has been sliced cleanly away, left drifting independently through space while the comet immediately begins forging a replacement tail. The most famous documented example occurred in April 2007 when NASA's Stereo spacecraft captured Comet Encke mid-disaster. A massive CME slammed directly into Encke's ion tail, snapping away in real time as cameras recorded the entire sequence. The footage has since become a cornerstone case study, replayed in heliophysics seminars and amateur astronomy forums worldwide. Scientists identify these events as magnetic reconnection, a sudden reconfiguration of magnetic field lines that drags the tail's ionized particles out of their structured alignment with the solar wind. For several hours, the comet appears tailless, a visual testament to the sun's invisible yet formidable power. With 7 comets crowding the ecliptic plane throughout late 2025, the probability of capturing another live tail disconnection has never been higher. Heliophysicists and amateur astronomers alike maintain vigilant watch, searching for telltale signs, a sudden kink in the tail structure, an abrupt break, or ghostly wisps of severed material left drifting behind. Each disconnection event offers a front-row perspective on the sun's extended reach, a vivid reminder that space weather isn't merely theoretical abstraction. It's written across the sky in real time, visible to anyone paying attention. Comet tails don't merely create beautiful photographs. They function as instantaneous space weather indicators. The reason lies in orbital geometry. During late 2025, most of the 7 comets follow trajectories threading close to the solar system's ecliptic plane, the flattened disk where Earth and other planets orbit. This shared orbital highway means that when the sun launches a coronal mass ejection, the probability of a comet intercepting that storm increases dramatically. It becomes a matter of straightforward geometric alignment. With numerous comets clustered near the ecliptic plane, each spends substantially more time positioned in the potential firing line of solar storms. Forecast models executed by heliophysics teams clearly illustrate the statistics. During a typical year, a bright comet might face a 10 to 20% probability of experiencing a visible tail disconnection during its perihelion passage. With 7 comets stacked along similar orbital lanes throughout 2025, those individual probabilities multiply considerably. Statistical projections suggest the season could deliver several tail disconnection events, potentially even 2 or more occurring within the same week. For observers, this represents far more than merely a crowded sky. Every CME that sweeps through the inner solar system becomes a roll of cosmic dice. If timing aligns precisely, the sun's magnetic field will slice through a comet's ion tail, producing an instantaneous severing, a visual confirmation that space weather has struck with full force. With so many comets positioned in optimal geometric alignment, the coming months promise an exceptionally rare opportunity to observe the sun's invisible hand at work, its effects written in luminous blue streaks across dawn and dusk horizons. The measurements arriving from the world's most powerful telescopes are genuinely staggering. Astronomers utilizing the Hubble Space Telescope and the James Webb Space Telescope have measured the coma of 3 Eyes/Atlas, its glowing envelope of vaporized gas and suspended dust, at nearly 700,000 kilometers in diameter. That figure isn't a typographical error. This single comet's coma spans nearly half the sun's diameter and exceeds Jupiter's width by more than 50 times. Imagery reveals a diffuse greenish sphere that utterly dwarfs the rocky nucleus at its center, a tiny fragment lost within a cloud vast enough to engulf planets whole. Yet physical size represents only part of what makes 3 Eyes/Atlas extraordinary. What truly distinguishes this interstellar visitor is its unprecedented activity level. As sunlight strikes the nucleus surface, jets of gas and dust erupt with astonishing violence. Measurements obtained from JWST and ground-based observatories calculate dust ejection rates at 6 kilograms per second for fine-grained particles, roughly equivalent to a bowling ball's mass every second, and up to 60 kilograms per second for larger fragments. These powerful jets carve out fans and streamers within the coma, sometimes shifting dramatically from hour to hour as new vents open and seal with the nucleus's rotation. The result manifests as a living, breathing structure, constantly reshaped by solar radiation pressure and space weather conditions. Imaging teams from Gemini South Observatory and Palomar Observatory have invested countless observation nights tracking these dynamic changes, digitally stacking lengthy exposures to extract subtle details embedded within the jet structures. Their work reveals a comet that demonstrates anything but static behavior. The jets flicker and pulse with remarkable variability, sometimes tracing graceful arcs hundreds of thousands of kilometers in length. Each outburst contributes fresh material to the coma, continuously feeding the extensive tails that stream far behind. Even at a distance exceeding 1 astronomical unit from the Sun, 3i/Atlas produces a display rivaling the most active comets ever systematically observed. The scale of this physical presence challenges human comprehension. For professional astronomers, it represents a precious opportunity to study cometary outgassing mechanics in real time using the most sophisticated instruments humanity has ever constructed. Every new image captured, every measured jet velocity adds another crucial piece to an evolving puzzle, laying essential groundwork for the next profound question. What exactly comprises this remarkable visitor? What occurs when a comet originating from another stellar system reveals chemistry that defies all expectations? Spectroscopists working continuously with JWST and the Spectropolarimetric High-Contrast Exoplanet Research, SPHERE, instrument have determined that 3i/Atlas fundamentally breaks established rules. Unlike typical comets where water vapor dominates spectroscopic observations, this visitor's coma floods with carbon dioxide in unprecedented proportions. The numerical ratios prove impossible to ignore. For every single water molecule detected, there exist 8 molecules of CO2, an 8-to-1 ratio that establishes a new record for any comet measured throughout astronomical history. The conventional script for bright comets predicts that water ice should dominate the composition, vaporizing readily as sunlight intensity increases, and forming the classic glowing tail structure. Yet in 3i/Atlas, water vapor appears almost incidental. Instead, carbon dioxide jets erupt violently from the surface, painting the coma that characteristic green hue and fueling intense debate among planetary scientists. Was this comet formed in an exceptionally frigid zone far beyond its home star's reach, where carbon dioxide could freeze out in massive quantities? Or does a thick insulating crust conceal substantial pockets of water ice, waiting for precisely the right thermal conditions to explosively emerge? The answer remains actively contested, with research teams meticulously analyzing every spectroscopic observation to extract the truth. This exotic chemistry transcends mere academic curiosity. If 3i/Atlas sheds CO2-rich dust particles as it approaches perihelion, the material it disperses along its orbital path could differ fundamentally from anything Earth has previously encountered. And there's an intriguing development approaching. N-body gravitational simulations demonstrate that after perihelion passage, the dust trail deposited by this interstellar traveler may intersect Earth's orbital path during mid-2026. Meteor scientists have already begun mapping the potential intersection geometry, drafting detailed observation plans for coordinated radar campaigns and airborne detection missions designed to capture even a single grain of authentically interstellar dust as it ablates in Earth's upper atmosphere. If successful, these ambitious efforts could deliver humanity's first direct sample of material forged within another stellar system, an unprecedented opportunity to analyze isotopic ratios and molecular structures untouched by our own solar system's 4.6 billion-year evolutionary history. For now, every fresh observation of 3i/Atlas represents a ticket to the frontier of planetary science, where the stakes involve nothing less than fundamentally rewriting our understanding of chemistry in worlds orbiting distant stars. Rumors propagate faster than comets themselves. Throughout the weeks preceding the 2025 comet convergence, Social media timelines filled with ominous warnings, sensational claims, and a steady stream of apocalyptic predictions. Here's what the actual data demonstrate. Every single comet in the 2025 lineup follows a precisely calculated trajectory, mapped and continuously refined by professional astronomers utilizing the world's most powerful telescopes and the Minor Planet Center's comprehensive global database. Not one approaches anywhere near intersecting Earth's orbital path, much less posing any collision risk whatsoever. The closest approach, executed by Comet Swan, places approximately 37 million kilometers distant, more than 90 times the Earth-Moon separation. The remaining comets pass at even greater distances, their trajectories bending smoothly around the Sun, governed exclusively by gravitational physics, and nothing more ominous. Expert panels from NASA, the European Space Agency, and independent research institutions have thoroughly reviewed all orbital calculations, checked meticulously for any possible gravitational perturbations, and published their comprehensive findings in open-access peer-reviewed journals. The verdict proves unanimous and unambiguous. No physical mechanism exists by which this comet cluster could trigger earthquakes, severe storms, or any of the disasters currently trending across online platforms. Gravitational physics operates identically to how it has functioned for billions of years. Comets remain icy remnants from the solar system's formation, not cosmic wrecking balls, threatening planetary catastrophe. The only phenomenon they're likely to influence is the number of people choosing to look upward during dawn and dusk hours. The message bears repeating clearly. This represents a rare celestial spectacle, not a threat to human civilization. The optimal way to experience it involves wonder and curiosity, not worry or fear, for those eager to observe a comet firsthand. The essential information involves knowing precisely where and when to direct your gaze. Step outside just before sunrise on October 21st, and you might witness the season's premier event. That morning, Comet Swan executes its closest approach to Earth at approximately 37 million kilometers distance. No telescope required if you possess genuinely dark skies and an unobstructed eastern horizon. Look low toward the east shortly before dawn begins brightening the sky. If current predictions hold accurate, Swan could shine as brilliantly as magnitude 2 or 3, rivaling the brightest stars visible overhead. Its tail, sculpted by the relentless solar wind, may stretch across a substantial portion of the pre-dawn sky, a genuinely rare treat for anyone willing to wake early enough to observe it. Several weeks later, evening twilight claims the spotlight. From November 6th through 12th, Comet Lemon glides into visibility within the western sky after sunset. This represents the classic evening comet scenario. No pre-dawn wake-up calls necessary. Simply locate an observation site offering a broad, unobstructed western horizon. Lemon could reach magnitude 4, potentially even brighter if outgassing activity surges unexpectedly. Under rural skies far from light pollution, that brightness level suffices for naked eye detection. Within urban environments, binoculars will help distinguish the comet's diffuse glow above the horizon. Optimal viewing occurs approximately 30 to 60 minutes after sunset, before the comet descends too low toward the horizon. For both observing opportunities, a quality pair of binoculars unlocks significantly more detail, revealing the comet's soft luminosity and the initial hints of tail structure. A small telescope enhances the experience further, exposing subtle structure within the tail and delicate color variations. However, sophisticated equipment isn't mandatory. A printed star chart, a smartphone astronomy application, or even a simple magnetic compass can help orient you toward the correct direction. Dress appropriately for the ambient temperature. Consider bringing a companion to share the experience. Most importantly, allow adequate time for your eyes to adapt to darkness, typically 15 to 20 minutes away from bright lights. Patience consistently rewards observers. Comets can brighten or fade unpredictably based on outgassing activity, and the visual appearance transforms noticeably from night to night. During a year when the sky delivers more than its typical share of surprises, these observation windows represent your personal invitation to participate. No prior astronomical experience required. The only genuine prerequisite is the willingness to look upward and embrace the wonder of what's unfolding above. The clustered arrivals possess no documented precedent across more than a century of systematic comet observation records. Scientists acknowledge that while the dust trail of 3I/Atlas may intersect Earth's orbital plane during 2026, absolutely no impact has it exists according to all published orbital dynamics models. However, why so many comets appear concentrated within a single season remains fundamentally unsolved. Current comet population models cannot fully account for this dramatic spike in arrivals. The accumulated evidence points toward a rare convergence shaped by both random statistical variation and substantially improved detection methodologies working in concert. As 2025 and 2026 unfold, the astronomical record will document not merely a statistical anomaly, but rather a unique opportunity for coordinated observation and transformative scientific discovery, all captured in real time for rigorous future analysis. The sky is offering humanity something precious, a front-row seat to cosmic theater that defies probability and challenges our understanding. The only question that remains is whether we'll accept the invitation to look up and bear witness to what unfolds above.